this property about quotient groups related to morphisms. So let me state that again. And maybe let me just recap the key points from the last lecture. Okay, so I'll just recap the key points. The first one was the definition of a quotient group. Definition of a quotient group. Okay. G a group, H a normal subgroup, then G mod H is the set of left cosets. I mean, left cosets is, I mean, we write it like that only to sort of satisfy our desire to be precise, but it's actually also left cosets. I mean, it's also right cosets. But yeah, left cosets of H and G. Okay. Such, okay, with the operation G1H times G2H by definition equals G1 G2H, which okay, which makes it into a group with identity element EH, which is the coset of E is just H itself, okay? And inverses G1 GH inverse is given by the coset. I mean, this is, we are discussing the inverse of the coset in the quotient group. Okay? And what we observed last time is that that would actually be the coset of the inverse of G. Okay, that's the first thing. The natural map G to G mod H, where a group element is sent to the coset containing it. So this is a natural map that comes from any equivalence relation, is a group homomorphism, surjective group homomorphism. That's the second thing. And we began proving the following statement. I mean, we said the following: let phi from G to G prime be a group homomorphism. Okay. Let H be the kernel of phi. It is a normal subgroup because it's the kernel of a group homomorphism. Then we showed that the function, I mean, that there is a well-defined function phi bar from the cosets of H, the quotient group G mod H to G prime, okay, in which a coset of G, little g, goes to phi of G. So this is what we showed, okay, that this is a well-defined homomorphism is something that we have shown. I mean, a well-defined function. Okay? So now, today, we will first show that phi bar is injective. Show that one. Phi bar is injective. And 2, phi bar is a group homomorphism. Okay, this is what I mean. This would complete the proof of the proposition from last time.
Sir,
Yeah,
could you scroll up to the last line for a moment?
I just wrote down the remaining sentences, assertions of the proposition that we were proving.
Yes, yeah.
I mean, the assertion was that there is an injective group homomorphism from G mod H to G bar, okay? Which, sorry, okay, we had one more thing. 3, phi is pi followed by phi bar. That actually came from the so this is what we will verify today. I mean, technically, yes. What we said, maybe I should just remind you what proposition that this is the given information. Okay, G to G bar. Okay, H is the kernel. So there's already, I mean, there's a known map from G to G mod H. Okay, and the assertion is that there exists a phi bar like this. Okay, phi bar, okay, such that phi is phi bar composed with. I mean, pi, sorry, I don't know what way correct. Pi followed by phi bar. This is what, and this is a group homomorphism. In fact, there is a unique group. Okay, maybe we should include that also in our claim. Such a phi bar is unique. So just to clarify, the injectivity of phi bar is a property of functions. The uniqueness of phi bar is again a property of functions. And so 1, 2, and 3 are really proved at the level of functions itself, without thinking about group homomorphisms. The group homomorphism is just, I mean, just follows from calculations. So let's prove this statement. So 1.
So 3 just follows from how we have defined it, right?
Correct. As I said, both 1, 3, and 4 actually follow from the definitions. I mean, I should not say 4. They I mean, 1, 3, and 4 hold at the level of functions between sets. All that we will check is that given 1 and 3, phi bar is unique as function. Yes. So we will not need to know that this is a group homomorphism to prove these statements. Okay. That's what that's what I meant by just saying. Okay. Correct. I mean, and none of these things are particularly difficult. The key point is to understand that there is a map from the quotient group to G bar. There's a function for the quotient group to G bar, okay? And how it is defined, because I mean, the way it was defined was so that the third property will hold. But let's check them one by one. Okay. So 1, we need to check that's injective. Maybe 3 is actually, yeah, maybe 3 is easier to check. Maybe let's check 3. 3 is easier to check. Okay. So pi of G of phi bar is phi bar of GH. Okay. But we've already said phi bar has the property that it sends G to phi of G for all G inside G. So this proves 3. I mean, this is what 3 is saying, and this is okay. So 3 is, so again, all that we're using is that from G mod H to G bar, G prime, there is a function that can be defined on the whole coset. I mean, and it's well defined. That's so now let's check one. So to check one, we need to show that. Okay, maybe yeah, sorry, I thought, sorry, maybe it is actually easier to check one than check. Okay, let's check one, since I wrote it as properties of function. Okay, so suppose that phi bar of G1H is equal to phi bar of G2H. Then what does this mean? This means that phi of G1 is equal to phi of G2, because right, phi bar of GH is these are, but what does this say? This says that G1 inverse G2 is inside H, which is the kernel. Right. Which means that G1.
Are we using that phi is a homomorphism here?
Phi is a homomorphism.
Oh, okay, yes.
Yeah. I mean, yeah, we have to use that phi is a homomorphism. I mean, of course, we cannot make these claims. Yeah. So maybe I should have been more precise. What I should say is that without knowing that phi bar is a homomorphism, we could prove the remaining statements. Okay. But now that I mean, that's how I prepared my lecture. But now that I'm lecturing it, maybe that is not the best way. It may have been easier to just check that that's homomorphic, because that check is independent of all these things. Okay. G1H G1H is equal to G2H. Therefore, phi bar is injective. So, yeah, sorry, I don't want to complicate this thing. One can, I mean, one doesn't need to use the third line in here and just work at the level of functions itself and prove this. Okay, so I will outline in an exercise how these things can be checked for functions. Okay. Maps between, I mean, just a function between two sets, why substantial part of this proposition will hold, except the things that explicitly refer to group homomorphism. Okay. That I will do in an exercise for this. I mean, yeah, it is important for us to also, I mean, when we see a proof like this, it is important. I mean, at least maybe for you, this is probably, for many of you, this is probably the first time that we are seeing sets, and now sets given extra structures. Okay? So typically when we see a proof, we should try to understand what exactly is the proof using. Okay? Does it hold in more generality than it would I mean, than it is written. Okay? So in that in that spirit, I will recast a substantial part of this proposition as a property of functions between sets, and I will include that in the exercise, which is, yeah. So phi bar is injective. So that proves that, and let's prove 2, and then we will worry about 4. Now we need to show that. We need to show that. I mean, we want to show that for all G1, G2 inside G, phi bar of G1 H, G2 H is equal to phi bar of G1 G1H times phi bar of but this is where the group homomorphism is. So this is phi bar of, I mean, G1H, G1H, G2H. So this is the product inside G mod H. That is same thing as phi of G1, G2, right? Which is pi of G1 times pi of G2. Okay. So now phi bar of this, phi bar of G1H, G2H. So phi bar of pi of this is just phi of G1, G2, which is phi of G1 times phi of G2. That's because phi is a group homomorphism. But what is this? This is phi bar of G1H times phi bar of G2H, which is what we wanted to do. Therefore, phi bar is a group homomorphism. So we have checked the first three parts of this thing. And the last part, uniqueness of phi bar. Okay. So suppose psi is another map psi from G mod H to G bar is such that psi composed with phi is phi. Okay. We need to show that psi is phi bar. Okay. So this implies that psi of G H is equal to phi of G for all G inside G, which actually implies that psi equals phi bar, right? Because that's exactly the definition of phi bar. So again, this is also done at the level of functions, not at the level of group homomorphisms. So this concludes the proof of this existence of such a map. Okay. So let us try to find some examples, okay? Not particularly. I mean, just which illustrates this one. Okay, some examples. From Z to Sn, okay, we can define a map. So Z is a cyclic group. Okay. If you tell, I mean, it's a cycle. Okay, we will. Okay, it is a cyclic group. It is an infinite cyclic group. So if you tell where one goes, I mean, zero. So let this be a group homomorphism. I'll specify what it is. So I'm going to write D group homomorphism. Okay. So let us see what we need to. Okay. Let us say that n goes to tau to the n, where tau is the permutation 1, cyclic permutation 1. Just an example. Okay. Now, I just want to remark here, okay, if you only just say, so this of course defines it as a function altogether for every element of Z. I mean, where does it go to? That is specified. Okay. If we had only said, I mean, not even if we had only said that phi is a group homomorphism with phi of 1 equals tau, okay, we would get the full, when we would get this unique, we would specify we would be specifying the exact group homomorphism. Okay, that is because Z is a cyclic group and everything is a multiple of 1. Because 0 goes to 0 is part of the group homomorphism data. And if 1 goes to tau, 2 must go to tau square and 3 must go to tau cube and so on. Yeah. See this? Okay, so therefore, often when we write, I mean, we will probably only just specify enough data so that we can understand, so that we can determine the group homomorphism unambiguously. Okay? To see this, note that, 0 must go to the identity, 0 must go to the identity permutation. That is always, that is always understood because this is a group homomorphism. And if 1 goes to tau, then n, which is 1 plus 1 plus 1 plus n times. Okay, assuming n is positive, must go to tau n times. Okay. So this is so often. Often one could just say that let Z. Consider the group homomorphism Z to this one, in which 1 goes to this tau. Okay. And that is unique. Okay. Okay. So consider this. So what is its kernel? Well, tau squared. This is a transposition. Okay. Tau squared would be 1. Okay, we see that 2 is in the kernel of 5. Okay, and tau is not 1. Identity permutation. So, this is identity. Okay. So 1 is not in the kernel. Okay. So therefore, kernel of 5 is equal. Kernel, we know that subgroups of Z must be generated by one element, smallest positive element in, they are either 0 or generated by the smallest positive element in that subgroup. Okay. In this case, it is 2. So this is all multiples of 2. Okay. So therefore, Z mod 2Z injects into Sn. Okay. And here we will just write a 1 bar to denote the residue class mapping to tau. Okay. Another example that we could in a similar vein. Another example that
you explain what that means. Injects into SN.
There's an injective group homomorphism. I'm sorry, it's bad English. Everybody uses it. Sorry. There is an injective group. There's an injective function, right? But we know we only put it's group homomorphism, right? Yeah, I agree. Nobody. I'm sure if you look at the dictionary, there's no meaning for the word inject the way I used it, but all of us use it. Okay, so yeah, we'll also say surgex on 2, but unfortunately, there's no. We just do it. Yes, I should say there is an injective group function or group homomorphism. Is that clear now?
Yes, sir.
Hello?
Yes, sir, it's clear.
Yeah. Yeah, we'll say, yeah. So sorry, yeah. So another example, Z2 S5. Okay, an example that you have, an example related to one of the calculations in one of your quizzes. Let us say 1 goes to 1, 2, 3, 4, So this is so if we these are disjoint cycles, they'll commute with each other, and so a kernel of this. Okay, so 6. Okay, so let's call this 5. Okay, so phi of 1 is just, let's call this thing sigma, or maybe I'll just call it sigma 1, sigma 2. Okay, so this is sigma 1, this is sigma. Okay. Phi of 2 would be sigma 1, sigma 2 squared. Okay. And because these are disjoint cycles, they will commute with each other. I mean, they're just acting on disjoint pieces of the set 1 through n. Okay. And that action is commute. So this is just sigma 1 square, sigma 2 square, which is sigma 2 square is 1 because it's a transposition. So this is just sigma 1 squared. 3 is similar, for similar reason, it is sigma 1 cube, sigma 2 cube, but sigma 1 cube is identity. So this is sigma 2 cube, and so on. We'll get that sigma to the 5 is not identity, but sigma 6, not sigma 5. 5 is not identity, but
sigma 2 cube is just sigma, right?
correct.
Sorry, sigma
Correct,
2.
you're right. Sigma 2, correct. This is identity. So therefore, kernel of phi is 6z, and therefore z mod 6z injects into S5, in which 1 bar goes to this thing, sigma 1. Okay, so this is a yeah. So there is an extremely important corollary of this thing.
So in these examples, we are just trying to construct a normal subgroup, right? I mean, we know the kernel to be normal, and that's what we are constructing.
I am just illustrating what the theorem says here. I am not, I mean.
Oh, okay.
Yeah, I mean, essentially, I'm just calculating what the kernel is. We know it's normal, and then therefore we know that Z mod the kernel will inject.
Okay.
Yeah, I am not. I am just giving some examples of what does this theorem tell us in that context. That's all. It is not. Yeah. Okay. So there's an important corollary of this thing. So let phi from G to G prime be surjective group homomorphism. Okay, so let me call it corollary 1. Then G prime is isomorphic to G mod kernel of phi. And corollary 2, let phi from G to G prime be a group homomorphism. Then image of phi is isomorphic to G mod kernel of phi. And these are related. We will prove corollary 2 from corollary. Corollary 1 itself we will prove from the proposition. Okay. Proof of corollary 1. So now we have a surjective group homomorphism, and we want to prove that some group is isomorphic to some other group. So the first thing, that is to prove that two groups are isomorphic, we need to find an isomorphism between them. We need to find a group homomorphism and prove that it is an isomorphism. So this is so I mean, typically if the maps are very natural, we don't write down what the function is. I mean, we may not specify what the function is, but in this case, but it is still required. I mean, when you claim that two things are isomorphic to each other, we need to give the function that establishes the isomorphism. So here we will do it that way. So we'll make we'll do a more precise statement. More precisely, we will show that the group homomorphism phi bar from G mod kernel of phi to G prime is an isomorphism. Okay. So in order to say that two groups are isomorphic to each other, we need to exhibit a function that is a group. That's a group isomorphism. So here we have a candidate that's already a candidate group homomorphism. We will just check that is an isomorphism. That is the and this itself is not very difficult. We know that it is injective. We have already shown that phi bar is injective. Okay. But since phi, which is phi followed by phi bar, is surjective, phi bar is surjective. Okay, so this is, do it as an exercise if you want. Some two functions f to y and g to z. If the composite injective, then f is injective. These are properties for functions. If the composite is surjective, then the second one is surjective. Okay. That's what I'm using here. The composite function is surjective. The second function is surjective. But that is okay. Therefore, phi bar is bijective group home. Yeah. Sorry, did somebody have a question? Which implies that phi bar is an isomorph. Yeah. Okay. So just okay. So although a priori, in the corollary, we only asserted that these two groups are isomorphic. In order to prove it, we need to exhibit a group homomorphism and show that it is an isomorphism, which is what we have done. We already had a natural group homomorphism. We just checked that it is an isomorphism. Corollary 2. Proof of corollary 2. Phi induces a group homomorphism. So maybe let's image of phi is a group, right? It is a subgroup of G bar, G prime. Okay. Phi induces a group homomorphism, surjective homomorphism from G to image of phi, which we still denote by phi. I mean, I'm being pedantic. Phi is technically a function from G to G prime. It is not a function from G to image of phi, because image of phi could potentially be a different set. It's a subset of G prime, but it is a different thing. It could be different. But ultimately, the thing comes only from G to image of phi, right? So that thing, it's still the map phi. So we will not use a new notation, but we'll just observe that that also is a group homomorphism. It's a surjective group homomorphism. Therefore, G mod kernel of phi is isomorphic to image of phi by corollary. Corollary 1 says that if you have a surjective group homomorphism, then it is the image is isomorphic. I mean, the target is isomorphic to source modulo the kernel, and here we have rewritten the given phi as a surjective group homomorphism onto the image. Therefore, it is isomorphic. Okay. Another way to think about this. So let me finish the proof here. Okay. Another way to think about this would be that phi bar is from G mod kernel of phi to G prime is a group homomorphism, is an injective group homomorphism. Okay. Therefore, by corollary 1, okay, G mod kernel of phi is isomorphic to image of phi bar. Okay, because it is always surjective onto the image. But here, in this case, it's also injective, so it's isomorphic. But note that image of phi bar is equal to image of phi. That's another way to think about the same. But ultimately, it comes down to this fact that if you have a surjective group homomorphism, then the target is isomorphic to the source modulo the kernel. Okay. So now, yeah. Okay. So this is some structure about group homomorphisms and things like that. I mean, there's. So the next thing that I want to do is what is called the first isomorphism theorem, which is to relate the subgroups of a surjective group homomorphism. I mean, sorry, let me just first isomorphism. Sorry, sorry, give me a minute. I'm slightly confused with that. Just give me a minute. Let me just quickly check what the book says. What is first isomorphism? I'm sorry, I got it wrong. What they call this is called the first isomorphism. I'm sorry. This is called the first. What I wanted to state was the second or third. Okay. So before I state the next isomorphism theorem, I want to state another property about quotient, these things. Okay. So let phi from G to G prime be a surjective group homomorphism. Let H prime be a subgroup of G prime? Observation. Phi inverse of H prime is a subgroup of G containing kernel of phi. So I hope the statement that I'm making is maybe I draw a picture before I start. So just schematically, this is G prime. This is G. Here, let me call it E prime, and this is E. And then there is a kernel here. And I'm looking at some H prime here, subgroup. And I'm looking at the pre-image. This is a subgroup of containing kernel of G. And again, just to remind you, phi inverse of H prime by definition is all G inside G, such that phi of G is inside H prime. It is not, so these are, I mean, one should not confuse them with inverse functions of bijective functions. Okay. So proof of the observation. So we need to show that it is closed under the binary operation and it contains inverses. So let G1 and G2, okay, so we can check that if G is inside kernel of phi, then phi of G is E prime, this is inside H prime, so G is inside phi inverse of H prime. Okay? Therefore, kernel of phi is a subset of phi inverse of H prime. So that's that we can check. Whatever it is, it contains kernel of phi. So we'll just check that it is a subgroup. Now let G1, G2 be inside phi inverse of H. So this implies that phi of G1 and phi of G2 are inside H prime, which implies that phi of G1 inverse is inside H prime because it's H prime is a subgroup, and phi of G1 times phi of G2 is inside H prime. But what are these elements? This is phi of G1 inverse. It's inside H prime. And this is phi of the product, okay, which implies that G1 inverse is inside H prime and G1, G2 is inside H prime. Therefore, H prime is a subgroup of G. Sorry, phi inverse of H prime is a sub. Oh, I'm sorry. Here I forgot to put the phi inverse. Okay, so this proves the observation. Any questions? Now, suppose we take something like this, a subgroup containing G prime, containing the kernel. And let us look at what it gives in G prime. Okay. So another observation. Let H be a subgroup of G containing kernel of phi. Then pi of H, which is just not pi, phi of H, phi of G, G is inside H. Just as set, if you just apply the function, is a subgroup of G prime. Again, not very difficult proof. I mean, once I tell you that this is what I want you to check, you will be able to check this. Okay, but so just think of this as me just telling you what all things we generally worry about when one studies these things. Proofs themselves are not very complicated. So we need to show that if you take two elements, so let us call it A and B be inside phi of H. Therefore, there exists G1, G2 inside H such that A is phi of G1 and B is phi of G2. Therefore, A inverse, which is phi of G1 inverse, this is inside phi of H, right? Because since G1 inverse is inside H, it's a subgroup. And AB, which is phi of G1, G2, is also inside phi of H. Okay. Therefore, phi of H is a subgroup. Okay. So there are two independent. So right now we have proved two independent things. One is inverse image of a subgroup inverse image of a subgroup is a subgroup containing the kernel. Conversely, if you take a subgroup containing the kernel and you look at its image, we would get a subgroup. It can. Okay, so we didn't. So I should clarify that we did actually use that it contains the kernel, but there is a reason why I wrote it like that. So now I will write what is called what is sometimes called the correspondence theorem. There is a bijective correspondence. In the context of the third. So let phi from G to G prime be a surjective group homomorphism. Then there exists a bijective correspondence between the following two sets. Okay, so right now we're just considering two sets and saying that there is a bijection between them. The first thing is subgroups of G containing kernel of phi. Okay. And the second one is subgroups of G prime. Okay. And so let me call these two sets X and Y. Okay. More precisely, let capital phi from X to Y, okay, that is the set of subgroups of G containing kernel of phi to subgroups of G prime, be the map which sends H to phi of H. And capital psi from Y to X be the map which sends some subgroup H to phi inverse of H prime. Okay, let phi be this and be this. Then phi and psi are inverse functions of each other. Okay. So subgroups of G containing kernel of phi, okay, they what in one-to-one correspondence with subgroups of G prime. Okay. Similarly, given any subgroup of G, and if you do it, if you start from, so what this one says is, if you start from something in Y, go to X, and then come back, you'll get the same element. That's why these are inverses of each other. Okay. So I will just sketch. It's not a very, given that we have checked these two independent observations, there's not much left here. So I will only just sketch this thing. So why we need to worry that it is surjective as well as, on one side that the group homomorphism is surjective, and the other one is that this one contains, that is, I mean, it is in the proof of this that part is used. Okay, so proof of this theorem, this correspondence theorem. So we have already checked that these are well, I mean, little phi of H is a subgroup of G prime, and this is a subgroup of containing this. So phi and psi are functions as they claim to be, from X to Y and Y to X. That we have checked using the previous observations. Okay. So we just need to show that these are inverses of each other. So let H be a subgroup of G containing kernel of phi. So then we are applying phi to it. Then we're taking phi inverse of that thing. Okay. So this is psi of phi of H. Okay. We're going from X to Y and back. Okay. This clearly contains H. Okay. This just means that every element of H goes to phi of H under the map phi. Okay. So it clearly contains H. Okay. So now suppose that there is some element in this. Okay. So now let G let G in G be such that phi of G is inside phi of H. In other words, G is in this phi inverse phi H, and we want to show that G is inside H. Okay, so we want to show that G is inside H. Okay. So, but what does this mean? Therefore, there exists G1 inside H such that phi of G is phi of G1, which implies that G inverse G1 is in the kernel of phi. Maybe I want to write it the other way around. G1 inverse, G1 is inside H, right? Yeah. G1 inverse G is in the kernel of phi. Okay? Because they both get mapped to the same element. But this is inside H. Okay? This is where it is used now. Therefore, G, which is G1 times G1 inverse G. G1 is inside H. This we just checked is inside kernel, so it's inside H. So this is inside H. Okay. So this is where the hypothesis is. Okay. So this says that. Okay. So therefore, if you apply phi and then you apply psi, capital phi and then apply psi, okay, this is the identity function on X. Any element of X goes to Y and comes back to the same element under this composite map. Okay, we need to show the other one also. Okay. So now let H prime be a subgroup of G prime. Okay. So in other words, H prime is inside Y. Okay. So now we will apply psi to H prime, and then we apply phi to this. Okay. So this is just phi of phi inverse of H prime. Okay. So now, what exactly can we say about this thing? By default, without worrying about, without checking all the hypotheses. So we are looking at an element of H prime, and then we are looking at every element in G that maps into this H prime under phi. And then we apply phi to that. So this is clearly inside H prime. Okay, that's the thing that, I mean, this is at the level of functions, the statement is true, and only this is true. Okay? Even in groups, it might only be that you won't get an equality, but we have to use the fact that phi is surjective. Okay? So just think about this statement. What we are doing is to apply phi to an element, okay, whose phi is inside H prime. Therefore, by definition, all that we can immediately conclude is this containment. So now we need to show the other. Okay? So now let some G prime be inside H prime. So we want to show that G prime is inside. Okay? Show that G prime is inside phi of phi inverse of H prime. Okay? But since phi is surjective, okay, and again, this is where the hypothesis is used. Surjective, there exists G such that phi of G equals G prime, which implies now that which implies that G is inside phi inverse of H prime, right? G prime is inside H prime, right? Which implies that G prime, which is phi of G, is inside phi of phi inverse of H prime. Okay. So therefore, equality holds here. Okay. So this gives us another. Sorry, that is not correct. Sorry. Okay. So this proves a theorem anyway. So this theorem is so we will see some. Yeah. Okay, so I'll put some exercises to illustrate how this theorem will be used. So that's so the next topic I want to discuss is group actions, but maybe I will stop. Sorry, let me just quickly check if there is some small example that I can do. I was. Just give me 1 minute. Maybe let me see if I can find some small example. Really not. This is just some very tedious checkings that one needs to do. But let's see if the book works out. One example. Okay. Groups of order 4. So let us now maybe do up to order 5. We can do. Okay, maybe we can do that. I thought this lecture will take longer than that, so I had not prepared these examples. But I think the small groups, because the next thing I want to do is group actions, which I don't want to start today. I will start next week. Okay, and then we will go on to proving zero theorem. I mean, group actions itself is an important topic. So we will try to do it, see as many examples as possible, sort of internalize the idea. Specific application that we have in mind is a proof of zero theorem. I mean, don't worry about the names. Okay, we will prove them. So let's do groups of smaller. Okay, so first a proposition. I mean, this is nothing to do with small order. In fact, it is very big order. If let P be a prime number, then every group of order P is cyclic. Some variation of this you would have done in your exercises, but let me anyway just prove this. Okay. So proof. Let G be a group of order P. So this will take care of 2, 3, and 5. Okay. We will do 4 separately. Let G be a group of order order P. So let G be inside G, G not the identity. Then we know that let H be the subgroup generated by G. Okay, so it is actually H is of the form E, G, G square, and so on. I mean, I don't need to write negative powers because this is a finite group. Eventually, they have to agree at some point. Okay, so this is just some finite set. Okay. Then we know that order of the group, the cosets of H have all of them have the same cardinality and they're disjoint. Okay, since the order of H divides order of G, which is a prime number. Okay, it says that order of H must be equal to P. I mean, since G is not, it cannot be 1, okay, because G is not directed here. Okay. So therefore, G equals H, which is therefore E, G, G square, all the way up to G to the P. Okay. I mean, G to the P is identity. That's what it just. I mean, it cannot be a smaller number that is equal to identity, because it is that is if that equals identity, then it should have a smaller size, but no smaller number will divide P, other than if it's, I mean, unless it is 1. but we know that it has more than one element. It has E and G which are distinct. Okay. So every group of order prime is a cyclic group. Okay. So therefore, and then I mean, okay, cyclic groups are abelian, okay, and we can have a map. So corollary, G is isomorphic to Z mod P, Z, with same notation as above. Okay. So the same idea that we used earlier, let proof the corollary, let phi from Z to G. I mean, so fix an element. So remember, look at this thing. We didn't actually care what this little g is. Only care that it is not equal to the identity element. Okay. So let G be inside G and G not equal to it. Let phi from Z to G be the group homomorphism which sends 1 to G. Then P, I mean, then kernel of phi is PZ. Okay. First check that PZ is inside the kernel. Okay. And if anything else is in the kernel, then it must be some n times Z and P must be in it. So therefore, P must be equal to n. So check that this is, so check this. You just need to know the structure of subgroups of Z to conclude the statement. Okay. So, therefore, Z mod phi
Sir,
bar.
could you repeat what the map phi does actually?
One goes to G, so then n goes to Gn.
Oh, okay. So G is any
G
non-identity
is fixed, yeah,
element.
yeah. Fix
Okay.
a G which is not identity element.
Okay. Okay.
Yeah, yeah. It doesn't matter which G you choose. The same, I mean, the same thing is there in this proof also. Every non-identity element has the same order, which is P. And we have used that. I mean, it follows from the proof, but yeah, this to G. And this is cyclic, right? We already said that every element is generated. I mean, this is a surjective. So this point, this is surjective. Okay, is an isomorphism. So this proves that every. Okay, so in other words, there is only one group up to isomorphism of order prime, which is Z mod PZ. So then the next question is, what about? So the next, okay, so we're looking at small orders, right? So this takes care of 2 and 3. Okay. I mean, there's only one group of order 1, which is just containing 0, okay, identity element. Okay. There's only one group of order 2, which is Z mod 2Z. There's only one group of order 3, Z mod 3Z. Okay. So now groups of order 4. So Z mod 4Z is a group of order 4. It's a cyclic. In fact, it is the cyclic group of order 4. I mean, the same sort of exercise will show that there is, I mean, given any integer, there is only up to isomorphism, there is only one cyclic group of that order, which is Z mod LZ. Okay. So I'll put that as an exercise. It's the same argument as one would do. If G is a cyclic group of order n, consider the map from Z to G, surjective map, I mean, like this. So there it is not clear that you can take an arbitrary G, or that there is that says that there exists a G such that every element is of the form G square, G cube, G minus 1, G minus 2, G minus 3, and so on, an identity element. Okay. And that exponent tells you what the group homomorphism should be. Okay. And this will, okay. So that I will put as an exercise. It will also give you this idea that in order to prove that two groups are isomorphic, try to come up with some natural function and then check that it is a bijective group homomorphism. Oh yeah, sometimes it's easier to, sometimes checking that it is a group homomorphism is already built into something. Then you just have to check bijectivity, or you have to put it as an inverse group homomorphism. Okay, so groups of order. So this is okay, so but what characterizes this? Okay, so therefore, so that is, let G be a group of order 4. Then, I mean, if G is cyclic, okay, this is if and only if there exists G in G such that the order of G is 4. Okay, then we know what G is. That's what I just wrote, that G is isomorphic to Z morphism. Okay, so this is an exercise. Okay. Otherwise, let G be G not equal to identity. This means that order of G equals 2 because it has to divide 4. It cannot be 1 because it's not identity. So it has to be 2. Can't be 4. Can't be 4 since not cyclic. And can't be 1. Can't be 1 since G is not identity. Okay, so it has to be a divisor of 4, and the only thing is left is 2. So let H be the subgroup generated by G. By little g. So then H order of H is 2. Okay. Index of H is also 2. We check that subgroups of index 2 is right. I mean, H has 2 elements, G has 4 elements. Therefore, we can only have 2 cosets, H and something else. So it's normal. Okay. Therefore, G mod H is a group of order 2. Okay. That is, G mod H is isomorphic to some to Z mod 2 set. Okay. But what data do we have now? So we have, okay, maybe H was, okay, let's call that element. Okay. So, okay, so let us, okay, so G has 4 elements. I'm just trying to enumerate them. E and G. Okay, so this much is what H is. Then there are 2 more elements. Okay, let us call it G1 and okay, and let us say that we are enumerating left cosets, so it is G1G. Okay, this is G1H. I'm partitioning G into the left cosets of H. Okay, so there's H and some G1H. And G1H will contain G1 and G1 times G. I mean, G1 is G1 times E and G1 times G is G. Okay, so this is how it would be enumerated. Okay. What about G1, GG1? That's also has to be an element in the group because of multiple. Okay. So let's just look at what that is. Okay. So G times G1. This is an element of the right coset. Okay. Which is okay. So what can this be? Well, what can this be? Okay. Let us write on all possibilities. I mean, the group has only 4 elements. They can be written like this. So we just need to figure out, I mean, potentially there is this element. It must be one of them. Which one can that be? G1 is identity implies that G1 is G inverse is inside H. That is a contradiction, right? because G1 is an element of the other coset, not H. G1 is G implies that G1 is identity which is inside H. That is also a contradiction. G1 is G1, which implies that G is identity, which is a contradiction because G was chosen to be a non-identity element. Therefore, the only option now is therefore G1 must equal G1G. Okay. And that is, and from this one can conclude that G is abelian. Okay, because now I mean, there are 4 elements: E, G, G1, and G1G, which is also equal to G1. Okay, so it's an abelian group. So every group. Okay, so the conclusion is that every group of order 4. I mean, cyclic groups are abelian. Now we have. Oh, sorry, I'm really over time. I'm sorry, I just got carried away. Every group of order 4 is abelian. Okay, this is not cyclic. This is, okay. In fact, let me just take, I hope you have no class at 11:50. I'll just take 2 minutes and finish this thing. Okay. Consider the set Z mod 2Z cross Z mod 2Z. Okay, Cartesian product. Okay. This can be made into a group naturally. So in which some A bar, comma B bar, that's what this will look like, plus C bar, comma D bar. Okay. Elements of this Cartesian product are ordered pairs. Right? So A bar, comma B bar, this is equal to A plus B, A plus C bar. So addition component wise, B plus C. Okay, so check this. Okay. I mean, substantially more general statements are true, but I just want to show in this example. Okay. So check that this is. So now we will define a map. So let phi from Z mod 2Z to Z mod 2Z. Sorry, not cross the Cartesian product to G. I mean this G. Okay. Be the map in which 0 bar comma 0 bar of course goes to identity element. That's the identity element here. Okay. 1 bar comma 0 bar goes to G. 0 bar comma 1 bar goes to G1. And 1 bar comma 1 bar goes to, there are 4 elements here, right? This, individually the sets have 2 elements. Cartesian product will have 4 elements. This goes to G, which is also equal to G1G. I mean, it is because it's a median that this makes sense. This is a group isomorphism. Okay. You need to check that it's a group homomorphism, and then it's clearly injective. And it's an injective map from a set of 4 elements to another set of 4 elements. It must also be surjective. So it is a bijective group homomorphism. Therefore, it's an isomorphism. Okay. So this is so therefore there are exactly 2 non-isomorphic groups of order 4. Z mod 4Z cyclic and Z mod 2Z cross Z mod 2Z. I mean, with the operation that we just defined there, abelian but not cyclic. So then that takes care of 2, 3, 4, and 5. 5 is prime. Okay. So the next thing would be 6. Now 6, we will show that there is a cyclic group, there's an abelian group. I mean, there's exactly one. I mean, sorry, it's not correct. There, of course, there's only one isomorphism. I mean, every cyclic group of order 6 is isomorphic to each other. So there's a cyclic. Then there is an abelian group which is not cyclic, and then there is a non-abelian group, which is the permutation group on 3 elements, S3. So we will so that we will do at some point. And 7 again is a prime. 8 we have to worry a little bit. Okay. So there is a group of 8 that we have not seen. At least, I mean, without proof, we have seen all groups of order 6. I mean, I have to prove to you that there's nothing else. There's only 3 of them. Okay. But 7 is back to prime. 8, there is even a group that we have not discussed. Okay, so that the list we are not even close to finishing it. So, but small numbers we'll try to figure out. But at the same time, I mean, some of these things I will delegate to exercises because I want to develop, I mean, group actions and silo theorems, etc., which is also sort of important. Okay, so I'll stop here. I'm extremely sorry for going so over time.
Thank you, sir.